What's up, my StatsRs? Michael Princhuk here, and welcome to another video over practice multiple choice questions for the AP Statistics exam. This is part 4 in a 4-part video series I have, and in this particular video, we're going to focus on nothing but probability-based questions. I get tons of comments on my videos and emails asking for help with probability because for most kids, it's the #1 topic that they struggle with the most in AP Statistics. So I created 10 multiple choice questions that all focus on probability. Some are easy, some are, a little challenging, and some are, quite difficult. But these are meant to help make sure you are ready for any probability question that could come up on the AP Statistics exam. So here's what you're going to want to do in this video. You're going to want to view the question, hit pause, try it on your own. Get out a scrap sheet of paper, do some work, see if you can come up with the right answer, then hit play and see if you get that answer correct. If you get it correct, just fast forward to the next question. If you get it wrong, listen to my explanation, watch me show the work, listen to how I explain the question. That way, if a similar question comes up on this year's AP exam, you'll be ready for it. All right, the AP exam is not that far away, so hopefully these questions are going to help prepare you. Best of luck. Hope everybody does really, really well this year. All right, let's dive into question number 31. All right, and the correct answer is A. So first we recognize that this is a binomial distribution. We are given the probability of success, in this case hitting a bullseye and a bow and arrow, which is 78%. And then we're given a set number of trials, that's 5. And the question asks for the probability that we get 2, exactly 2. Now on the AP Sets formula sheet is the probability distribution for a binomial distribution. We see it here in this second row, and we're given everything we need. In this first box right here, we're given the formula to calculate probabilities. We're also given the mean and standard deviation for a binomial distribution, but for this problem, we need to know the formula to calculate probabilities. So the formula we're going to start off with is finding the probability that there are exactly 2 out of 5 successes. So we have 5 choose 2. 0.78 is the probability of success squared, because we need 2 successes. 2 times it's got to hit the target. And then 0.22 raised to the third. So what is that? Well, the 0.22 is the probability of failure. There's a 78% chance of hitting the target, 22% chance we don't. And why do we need 3 of those? Because there's 5 attempts, and if 2 of them have to be successful, that means 3 are unsuccessful. So that right there is going to generate the formula. Now, there's lots of different shortcuts on your calculator. Other, the TI-84 or the numerics calculator can do shortcuts to get the actual decimal answer. But as we look at the question, we're actually presented with the formula. They want to make sure you know the formula, and that's going to lead to choice A being correct. All right, let's look at question number 32. And here the correct answer is C. Now, this can be actually a little bit of a tough one, so let's make sure we understand. So it's a very similar problem, right? 78% chance we hit the target, and we have 5 attempts. But this question is asking for the probability that she hits the target at least once. So we first have to make sure that we understand what at least once means. At least once means 1 or more. So out of 5 attempts, that'd be 1 or 2 or 3 or 4 or all 5. So one way we could do the problem is to calculate each of those probabilities using the binomial distribution probability formula. So here you see all of that work for 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, 5 choose 5. But we actually don't see that work amongst our choices. So what's the other way to do this problem? Well, think about it. The opposite of at least 1 would be not 0. So if we find the probability of not 0, right? So it'd be 1 minus the probability of 0. So if we first take the time to calculate the probability of 0, 0 makes, that's not what we want. At least 1 means 1 or more, but the opposite of that is 0. So if we find the probability of 0, we then take 1 and subtract that probability, getting rid of it, and we'll be left with 1, 2, 3, 4, 5. One other way of looking at this is this, right? When she shoots 5 arrows, she can make 0, 1, 2, 3, 4. Whoop, I skipped 4 or 5. Now, the first question that we already addressed asks just for 2. Okay, great. Well, this question asks for at least 1, which is 1 or more. So we could calculate those probabilities, each of those, 1, 2, 3, 4, and 5, and add them all together to get our answer. Yes, that's awesome. But we could also calculate the probability of 0. That's what we don't want. And then if we take that approach, we then have to do 1 minus that to be left with what we do want. So using the probability formula, we have 5, choose 0. That'd be 0.78 to the 0, and that'd be 0.22 raised to the 5th, because all 5 arrows must miss the target. Now, 5 choose 0 is 1. There's only one way that can happen. They're all misses. 0.78 to the 0, anything raised to 0 is 1. So that would be just 1 times 1, which is 1. So essentially we get 1 minus 0.22 to the 5th. 0.22 to the 5th is missing all 5 of them. 1 minus that would mean we make at least 1. So that's how we come across the answer, choice C. A little bit of a tricky one, kind of hard to understand, so hopefully that makes sense to you. Now let's move on to question number 33. And the correct answer is B. This is actually a fairly easy formula that involves our addition formula. So anytime you see the probability of in this case we have the probability of stats, then we have the probability of calculus, then we're given the probability of stats or calculus, right? This is going to be a classic addition formula problem where we know that the probability of A or B, this is the little symbol right here for or, equals the probability of A plus the probability of B minus the probability of A and B, which is both of them. So in our particular problem, this would be the probability of stats or calculus equals the probability of stats plus the probability of calculus minus the probability of both. And then all we got to do is play the fill-in game. So the probability of stats or calculus is 0.58. That was given to us right here. The probability of stats was 0.42. That was given to us. Plus the probability of calculus, that was 0.20. That was given to us. And then typically in math, when we don't know something, we label it with an X. So the probability of stats and calculus, I'm going to call X. And now I just got to solve a pretty simple equation for X. Subtract the 0.42, subtract the 0.20, and we get negative 0.04. But we also have this negative left on the X that we have to get rid of, so you can multiply or divide both sides by -1, and we get X, or the probability of stats and calculus, is 0.04. Knowing how to use that addition formula is definitely going to come up on some multiple choice question on the exam, I promise. Moving on to question number 34. And the correct answer here is D. Now, this question deals with the sampling distribution. How do I know that? Well, I'm given the mean of a population, I'm given the standard deviation of a population, and then I'm given a sample size of 40. So I'm not dealing with individuals, I'm dealing with the mean of a sample, which is exactly what sampling distributions for sample means represent. So the first thing I have to think about for me to address this question is, all right, what is the mean and standard deviation of that sampling distribution for samples of 40 wrenches? Well, here are the formulas that can be found on the AP Stats formula sheet. So the mean of a sampling distribution equals the mean of the population. Okay, that makes sense. And the standard deviation of a sampling distribution for means is the standard deviation of the population divided by the square root of your sample size. Yes, one wrench may deviate by 2.3 ounces, but the mean of 40 wrenches should be much smaller, which is why we divide by the square root of our sample size. So first, let me do that math. So the mean of our sampling distribution should be 22.5. That's because that's the truth. The standard deviation of our sampling distribution for samples of size 40 would be 2.3 divided by the square root of 40, which is 0.3637. Now, what about the shape? Well, the central limit theorem says that if your sample size is 30 or larger, the sampling distribution for sample means will be normal. That means I can now use the normal model to find the probability. So the question is asking the probability that a sample mean of 40 wrenches is greater than 23 ounces. So what I first need to do is figure out the z-score, because find the probability that a mean is greater than 23 ounces would be equal to the z-score for what 23 ounces is in this sampling distribution. So to find that z-score, we're going to take 23 minus the mean, 22.5, divided by the standard deviation, 0.3637 for our sampling distribution, and I get a z-score of 1.375. And whether you use a z-table, normal CDF on your TI-84 calculator, or the normal app, the normal distribution app on your numbers calculator, the probability that a z-score is greater than 1.375 is 0.0846, leading us to our answer of D. So pretty good problem there. Usually there's always going to be a problem related to sampling distributions on the AP Statistics multiple choice test. So this is a good practice to understand that. You have to be able to understand the mean, the standard deviation, and then find the z-score for what you're asked about, in this case 23 ounces, and then go ahead and find the probability that we are greater than that. And now moving on to question number 35. And the correct answer here is B. The probability that the horse wins 0 races is 0.675. The probability the horse wins 1 race is 0.1875. And the probability the horse wins 2 races is 0.1375. Now let's walk through how to do this. The easiest way to understand this, I think, is with a tree diagram. So we have a horse, and we know that that horse is going to enter the first race, and we were told there's a 25% chance that that horse wins the first race, which means without me being told, I automatically know there's a 75% chance the horse loses that first race. So here are those 2 results. Now, the other probabilities in the problem were conditional because they have the word if. If the horse wins the first race, okay, that would be this top branch, there's a 55% chance the horse wins the second race, which means 45% it loses. Obviously, 1 minus 0.55 is 0.45. Then there's another conditional probability. If the horse loses the first race, okay, that takes us down this bottom branch, there's a 10% chance that that horse wins the second race, which means 90% chance they lose the second race. Now, let's count wins. The first row is 2 wins. They win. The horse wins the first, the horse wins the second. Now, multiply those 2 probabilities because we have multiple events, multiple races, multiply. So 2 wins would be 0.25 times 0.55 or 0.1375. Now, the bottom branch would be 0 wins. Lose, 0 total wins. That'd be 0.75 times 0.90, 0.675. Now, the middle 2 branches both result in 1 win. Win the first, lose the second, 0.25 times 0.45, or lose the first, win the second, 0.75 times 0.10. Now, because both of those end with winning 1 race, we would add those 2 results together to get the total probability of 1 win. Because again, both of those branches can happen at the same time, so it's one or the other. So we add those 2 probabilities together, 0.1125 plus 0.075 to get the 0.1875. And that is, of course, how we got that final answer of choice B. All right, moving on to question number 36. All right, here the correct answer is E. And this is actually a really easy question that a lot of kids struggle with. So here's the deal. This is a geometric probability because we know the probability of success. Successfully getting that gold card is an 8% probability. Now, we're asked to find the probability at the first. Anytime you're talking about the first success, that's going to be geometric. We want the first pack containing that gold card to be after the 5th pack open. Now, a lot of kids will sit there and try to do all this math to try to figure this problem out. It's actually really, really simple. Here's the deal. If we want the first gold card to be after the 5th pack, that means the 1st, 2nd, 3rd, 4th, and 5th pack must all be failures. So really, that's it. If the first gold card is after the 5th pack, the first 5 must all not be gold. Now, if gold is 8%, not gold is 0.92. So that'd be 0.92 raised to the 5th or 0.659. That's it. Now, a lot of kids ask, but what about the win? Don't I need a gold card? Don't I need that successful gold card somewhere? But the question doesn't tell me where that successful gold card happens. It could be the 6th or the 7th or the 8th or the 9th or the 10th or the 11th, ... towards infinity. So all I know for this scenario to be true is that pack 1, 2, 3, 4, and 5 must all be failures. Quite honestly, I don't care when I get my first gold card as long as the first 5 are failures. So that's how I get the answer of 0.659. Now, I'm going to be honest, there are other ways to do this problem. We could figure out the probability that happens on the first pack, then the second pack, then the 3rd, then the 4th, and the 5th. But that's not what we want. So we can add all that together and then do 1 minus that result. But that's going to take way more math. This makes way more sense. And it's actually really, really easy to do. And moving on to question number 37. And the correct answer here is B. This is another pretty easy problem that does challenge students. But the issue with this problem is it's a conditional probability. So as long as you know how to do the conditional formula, which is also on the AP Stats formula sheet, this question can be actually quite simple. So first, what is it asking? It's asking to find the probability that the person buys 4 tickets. That a randomly selected person buys 4 tickets, but there's a condition, given that they buy at least 3. So first, let's make sure we can write that out. So the probability that they're asking for is that the number of tickets is equal to 4, but there's a condition, and that's what this line is for, right? We use this line right here for conditional probability. And after that line is the condition that the person must buy at least 3, which means 3 or more. So t is greater than or equal to 3. Now, here's where we got to be careful using the conditional formula. In the denominator of the conditional formula is just the condition. The probability that the total number of tickets sold is greater than or equal to 3. So greater than or equal to 3 would be any of these outcomes, 3 or 4 or 5 or 6 or 7. So we add all those together and we get 0.72 in our denominator. That's the easy part. Now the numerator is that the probability is both, right? Both the condition and the question. So it would be the probability that the number of tickets is equal to 4 and greater than or equal to 3. So and is overlap, right? So here is greater than or equal to 3. That would be 3 or 4 or 5 or 6 or 7. And then the other thing that we're told is that we have to be equal to 4, which is right here, 4. So the overlap between those two statements, equal to 4, or anything 3 or greater, the overlap is 4 because equal to 4 is also greater than or equal to 3. So our numerator is actually just 0.35. So the numerator is 0.35, the denominator is 0.72, anything greater than or equal to 3, divide and we get 0.486. So that's a question that's really, really simple if you know that conditional formula and you know how to use it. But for a lot of kids, they kind of struggle understand the language of it, especially that numerator. They're like, I don't understand how the numerator is just 0.35. I thought it has to be 4 and greater than or equal to 3. Yeah, but the only number that is both equal to 4 and at the same time greater than or equal to 3 is 4. That's why the probability of the numerator is just 0.35. So pretty good question. All right, moving on to number 38. And the correct answer here is A. Now, this is another problem that involves a sampling distribution, but this time it's a sampling distribution for sample proportions. So we know that the population proportion is 65%. 65% of all teachers feel that social media is making bullying worse. But now we're going to look at samples of 120. And a sample or the proportion from a sample of 120 teachers does not have to be 65%. It could obviously be more, it could be less, right? Because samples vary. So what we have to do is think about the sampling distribution for sample proportions. Now, the mean of all sample proportions should be equal to the true population proportion, which should be 65%. We would expect the sample of 120 teachers to come back 65%, but samples are going to vary, so the standard deviation of the sampling distribution for sample proportions is going to be using this formula, which again can be found on the AP Stats formula sheet. It's a square root of p times 1 minus p divided by n. So filling in everything that we know that the population proportion is 65%, which means that would be the center of our sampling distribution. But we also know that samples are certainly going to vary. Some can be more, some can be less. So when we do the math, we get 0.0435 for our standard deviation of that sampling distribution. Now we have to actually answer the question. The question asking us that the probability that that sample proportion of 120 teachers is less than 60%. So let's go ahead and do that. The first thing we have to do is get the z-score for 60%, and that's going to be taking 60% minus what we expected, and that was the mean, divided by the standard deviation of our sampling distribution, and we get a z-score of negative 1.149, and then we could use our z-tables, we could use normal CDF on our T84 calculator, or we could use the normal distribution app on the Numerics calculator, but the probability of a z-score being below negative 1.149 is 0.125. So there's a 12.5% chance that a random sample of 120 teachers comes back 60% or less that thinks social media is making bullying worse. So this question dealt with a sampling distribution for sample proportions. Earlier we saw a question dealt with sampling distribution for sample means. They both might be in the exam or just one might be in the exam, but I promise somehow, some way, both of these types of things will come up for sure. All right, moving on to question number 39. All right, and the correct answer here is D. Now, I gotta be honest, this is probably the hardest problem of all 10 in this video. This is a problem that's gonna really make you think and challenge. So let's break it down so we can explain how I got choice D. Hopefully you did too. This is a pretty good one. All right, so here's what we know. We know that there's a 35% chance of snow and there's a 65% chance of no snow. Now, let's talk about what they told us. First, they told us that if there is no snow outside, which 65% chance tomorrow, but we do know that there's mean of 12 minutes to walk to school and a standard deviation of 2.5. Okay, cool. And if there is snow, which 35% chance of snow tomorrow, we know that there's a mean of 18 minutes to walk to school and a standard deviation of 2.1. So we have two different things that can happen. There could be no snow or there could be snow. And we know the probability of what's going to happen tomorrow, 35% chance for snow, 65% chance for no snow. And then we also know the mean and the standard deviation for the amount of time it's going to take to walk to school in those two different conditions. Now, the question's asking us for the probability that it takes more than 15 minutes. So what we have to do is calculate the probability it takes more than 15 minutes in each scenario. So let's start with the no snow scenario. The probability that it takes more than 15 minutes to walk to school, well, we have to first find the z-score for 15 minutes by subtracting the mean of 12 divided by the standard deviation of 2.5. We get a z-score of 1.2, and we were told that it follows a normal distribution. So again, we could use a normal table, normal CDF on a 1084 calculator, or we could even use the normal distribution app on the numerous calculator, but the probability that a z-score is greater than 1.2 is 0.1151. So if there is no snow tomorrow, there's an 11.51% chance of it taking more than 15 minutes to walk. All right, what about the scenario where there is snow? Okay, if there is snow, once again, we have to find the probability that it takes more than 15 minutes to walk to school. So we got to get the z-score for 15 by subtracting 18, the mean, divided by the standard deviation of 2.1. We get a z-score of negative 1.4286. And the probability that a z-score is greater than that is 0.9234. Again, use your normal table, normal CDF, or use your apps on your calculators. So if there is no snow tomorrow, 11.51% chance of it taking longer than 15 minutes. If there is no snow, oh, that should say snow. Sorry about that. I crossed it out earlier and I forgot to cross it out there. If there is snow tomorrow, there's a 92.34% chance that it takes longer than 15 minutes. But here's the deal. We don't know. Is there going to be snow tomorrow or not? If we knew for sure that there was no snow tomorrow, there's our answer. If we knew for sure that there was snow tomorrow, there's our answer. But we don't know. It's variable. So now we have to simply think about those two situations. Okay, the first situation is there is no snow and then it takes longer than 15 minutes. Now, this right here cannot happen unless the 0.65 happens first. That's when we have to multiply them together. If there is snow, which is a 35% chance, then the probability that it takes longer than 15 minutes is 0.9234. Once again, why are we multiplying? Because this cannot happen unless this happens first. But we don't know which one of these situations is going to happen. It's one or the other. That's why we add them together to get our grand total probability that it takes more than 15 minutes for us to walk to school tomorrow. And that's how I got the 0.398. So very, very difficult problem with tons of steps. There's at least 4 or 5 steps there. But it all starts off with being able to calculate the probability in this situation, being able to calculate the probability in this situation, and then understand that this situation happens at that 65% chance. This situation happens at the 35% chance. I don't know which one's going to happen, so we multiply and add together. Pretty difficult problem, and I hope I did a good job explaining it. Maybe not the best ever, but hopefully pretty good. All right, and finally, question number 40. Here it is. I made it a fairly easy one to end with. All right, and the correct answer here is B. Now, for some kids, this is easy. To others, it might be difficult, but let's walk through it. So first, I see the probability of A. I see the probability of A or B. I'm asked to find the probability of B. This is definitely something I'm going to need the addition formula. So here is that probability addition formula where we have the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. Now I'm going to start filling everything in. This is where you got to really, really listen. So first, the probability of A is 0.25. That's right here, nice and simple. The probability of A or B is 0.64. That's right there, nice and simple. And I don't know the probability of B. And what do we do in math when we don't know something? We put an X in its spot. So that's why there's an X right there. Now, here is the kicker. If the two events are independent, and I mean only if they're independent. If they're not independent, I cannot do this. They must be independent. And of course, the problem said they are. If they're independent, the probability of A and B equals the probability of A times the probability of B, only if they're independent, which in this case they are. Which means the probability of A and B, this back part right here, would be the probability of A, 0.25, times the probability of B, which I don't know, and remember I'm calling it X. So 0.25 times X is the probability of A and B, only because I know they're independent. If I didn't know they were independent, I would not be able to put anything back here. It'd be a giant question mark. I wouldn't know what it is. But because they're independent, the probability of A and B is A times B. 0.25 is A, and B I'm calling X. All right, now it's just simple math. So the first thing I'm going to do is subtract the 0.25 over, and I get 0.39. Then I have the 1x right here. That was from the probability of B. I didn't know what the probability was. I just called it X. Minus 0.25x. That was from this back part. No, those are like terms. Those both have an x, so I can combine them. 1x minus 0.25x is 0.75x. It's that easy. And for a lot of kids, they're like, wait a minute, this isn't algebra class, this is stats. Yeah, but I do need a little bit of algebra to understand that. All right, now I just have one step to solve for x. I have to undo multiplication, and to undo the multiplication of 0.75, I'm going to divide by 0.75. So 0.39 divided by 0.75 is 0.52, and that's my final answer for B. All right, that's a pretty good question, but the most important thing that you have to understand for this question is that I'm only allowed to do A times B to get the probability of A and B if they're independent. And that's exactly what it said in the problem, and that's how I was able to put a 0.25 times X for the probability of A and B. All right, 10 really good probability questions. Hopefully they're going to make you super prepared to do really, really good on the AP exam. See you later.